Hello everyone and welcome to Paragon Pathfinders. In today's interesting physics lesson, I'm going to teach you an interesting physics phenomenon called the Doppler effect. This name sounds quite complicated and complex, but trust me, it's one of the things we experience in our daily lives, which we do not even know much about. So what does the Doppler effect mean? We can see that from here, the Doppler effect is a phenomenon in physics where the frequency of a wave appears to change when the source of the wave and the observer are moving relative to each other. Okay, before I go ahead and explain this important concept, I want you to know that at the end of this introduction, we are going to solve a past question to solidify our knowledge of the Doppler effect and apparent frequency. Okay, let me go ahead and explain. Sometimes, while standing by the roadside, you might hear a siren blaring towards you. This siren might be from a police vehicle blaring towards you as maybe you returning from school or you're starting to buy something and it comes towards you. As it approaches you, the sound from the siren tends to be high pitched, and as it passes by, the same sound tends to be low pitched. Now, why is that? That is a Doppler effect in action. I believe you know what I'm talking about, right? Because we tend to experience this almost every day in our lives, where as a sound approaches you, you are the observer and this is the source. As the sound approaches you, it tends to be higher, right? The sound tends to be higher, but when it crosses or passes by, it tends to be lower. So this is the Doppler effect. Now, why is that? You can see that from this pictorial representation of two observers. One is on the left and this is on the right. So this red dot here represents the source, and these waves here represent the sound waves emitted by the source. You can see that this person here on the right will hear a higher pitched sound than the person on the left. Now, why is that? It is because the waves are compressed. As they approach the first observer, they tend to be compressed because this source is moving towards this observer. So the waves are going to be compressed. But as the source leaves the second observer, the waves are going to spread out. So it becomes less frequent compared to this. So that is why the Doppler effect happens. And we see this in our day-to-day lives. Okay, now the frequency that these two persons hear as this, let's say this vehicle or this source approaches the first observer and leaves the second observer is called the apparent frequency. Apparent in the sense that it is not actually the true frequency, but it is the frequency as measured or as observed by these observers. So that's the meaning of apparent frequency. It is not actually the true frequency emitted from the source, but it is as observed by these people who are close to the source. Okay, so how do we calculate apparent frequency? Because it's a very interesting topic in physics that always comes often in exams. So you should know how to calculate apparent frequency in order to do well in your physics exams. All right, how do we do that? To calculate apparent frequency, remember I told you that apparent frequency is not actually the true frequency emitted by the source, but it is the frequency as observed by the observer. Remember that the source might be stationary, the observer might be moving and all that. So it's not really constant. It changes as either the observer or source changes position. So how do we calculate this apparent frequency we are talking about? The formula to calculate apparent frequency is given us F prime is equal to Fs multiplied by V plus V sub O all over V minus V sub S. Wow, this formula might look complicated to you, but trust me, it's easy to use and it's simple and straightforward. Now, let me go ahead and explain the variables here in this formula. So this F prime simply means the apparent frequency. That's the meaning of F prime. It is apparent frequency. And this Fs simply means frequency of source. This is the true frequency as emitted by the source, where the V here is the speed of sound or the velocity of sound in air. The velocity or the speed of sound in air is approximately 343 meters per second, or we can say it's 343 meters per second. It also depends on certain conditions like temperature and all that. While the V sub O is the velocity of the observer. The denominator, the V here also means the speed of sound in air, which is also 343 meters per second. While the V sub S is simply the velocity of source. Okay, now let's look at some important scenarios where this formula would change. Yes, this might be the standard formula for calculating the apparent frequency, but it changes over time because of the position of either the observer or source. All right, let's go ahead and look at different cases where this formula might change. This general formula for calculating the apparent frequency is actually used when the source and the observer are moving towards each other. If you have such a case where they are moving towards each other, then it remains as it is. You can find the apparent frequency by plugging in your given values to find a solution to it or to get the required value. But in some cases, for example, let's assume that the source and the observer are moving away from each other. So let me use this to denote the observer. So this is O and this is S, the source and the observer. If the source and the observer are moving away from each other, then the velocity of the observer becomes negative. It becomes a negative value, while the velocity of source also becomes negative. Now, why is that? They are going in separate directions. So the waves are going to spread out the more, and the observer will hear less of that sound. So if the observer moves in the opposite direction with the source, or if they're both moving in the opposite direction simultaneously, then their velocities are going to be negative. Now, what happens? So the apparent frequency will now become, the formula for the apparent frequency now becomes, this is a speed of sound in air. Instead of putting a positive here, it now becomes a negative value because the observer is moving away from the source. It now becomes V minus V sub O all over V. So remember that the standard formula contains a negative sign below. So it's now going to be negative multiplied by a negative becomes a positive. So you now have this very formula. So this is used to calculate the apparent frequency when the observer and source are moving away from each other at the same time or simultaneously. So we can say that this is our case 1, This is our case 2. So let's talk about case 3. For our case 3, this is a situation whereby the, the observer is stationary, standing at a place, right? While the source moves towards it. The observer stands at a place while the source moves towards it. In this case, what do we say? The velocity of the observer is going to be 0. Yeah, because the observer is stationary, and if the observer is not moving, it means that his or its velocity is 0. But for the source, it becomes positive. It's going to be positive because the waves are going to compress, and as it is moving towards this observer, he will hear more of that sound. Okay, so this is for this very case, if the source is moving towards the observer while the observer is stationary, the velocity of the source will be positive while the velocity of the observer becomes 0. Hence, this formula will now become f prime is equal to fs, that is frequency of sound, and it's going to be multiplied by. Okay, so since this one becomes a 0, we're not also only going to have a v at the top, because if the velocity of the observer is 0, it simply means that this v here now becomes 0. So it goes away, and we're now left with v minus v sub s. Yes, it still remains v minus v sub s, because negative multiplied by a positive value is a negative value, right? So that is why it remains like as it is. Remember that this is a standard formula for calculating the apparent frequency. And if it is moving towards the observer, even though the velocity is positive, if you multiply that positive by this negative here, you get a negative value. Hence, if the observer is stationary and the source is moving towards it, this is a formula to use. Okay, let's explore others. Let's go to 3, 4, 5, 6, and all that. So for the fourth one, in a case where the the source is stationary, it's not moving, and the observer moves towards the source, what happens? What will be the formula? In this very case, let's analyze it. So the source is stationary while the observer moves towards it. The velocity of the source is going to be 0. So v sub s is going to be 0, while the velocity of the observer is going to be positive. Yes, it's going to be positive because it's moving towards the source. So the waves are the sound waves are gonna be higher or more compressed as he approaches. All right, so his velocity is going to be positive, while the velocity of the source will be 0. Hence, from this formula, we're now going to get that the apparent frequency is equal to fs multiplied by, remember that this is positive, so it will also remain positive. And for the denominator, remember that the velocity of source is 0, so it goes off. Hence, we have this to be the formula when the source is stationary and the observer moves towards it. Okay, let's look at the fifth case. Okay, in this very case, this is a situation whereby the source is stationary while the observer moves away from it. As the observer moves away from the source, the velocity of the observer is going to be negative because it's going away from the source, while the source velocity becomes zero because it's stationary. Hence, this formula will now become, this is equal to Fs multiplied by, so this negative multiplied by the positive value in the standard formula will give us V minus V sub O, and the denominator will be only V because the velocity of source is zero when it is stationary. Hence, this becomes the formula when the source is stationary and the observer moves away from it. And finally, this right now is a sixth case. So to calculate the apparent frequency in this very case, where the observer is stationary and the source moves away from it. So this is a source, and here we have the observer. So if the observer is stationary and the source moves away from it or from him, in this very case, the apparent frequency formula now becomes Fs, which is the frequency of source. For the observer, the velocity is zero because he is stationary. We're going to have our V, which is the speed of sound in air, all over. For this part here, we have our velocity or speed of sound in air as well. Remember that this formula has a negative value already, and as the source moves away from the observer, its velocity is going to be negative, right? It's going to be negative at this point because it's going away from the observer. And if you multiply the negative value by the negative value in the standard formula, you're going to have a positive value. Hence, this is a formula for calculating the apparent frequency when the source is moving away from a stationary observer. All right, let's go ahead and answer one past question to solidify our knowledge and understanding of the Doppler effect. All right, let's go ahead and solve an interesting past question on the concept of Doppler effect. The question reads, an ambulance with a siren frequency of 1000 Hz is moving at 20 meters per second towards an observer who is also moving towards the ambulance at 10 meters per second. Assume the speed of sound in air is 343 meters per second. Part A. Calculate the observed frequency of the siren sound for the observer. So the part A says we should calculate the observed frequency of the siren sound for the observer. And 2, if the observer stops, what will be the new observed frequency? Okay, let's go ahead and collect our data and then go ahead to solve this interesting question on Doppler effect. So our data, we have the frequency of source. This is equal to 1000 Hertz. So frequency is measured in Hertz. That's the SI unit for frequency. And then we also have the velocity of source, which is our Vs. This is equal to 20 meters per second. We also have, or we're also given the velocity of observer. This is 10 meters per second, and that's going to be used for the first part. we have the speed of sound in air, which is 343 meters per second. All right. Now, the first part says we should go ahead and calculate the observed frequency of the siren for the observer. All right, let's go ahead and solve this interesting question having listed out the given parameters. Since they are both moving towards each other, we are going to use the standard formula for calculating the apparent frequency, which is f prime is equal to frequency of source multiplied by the speed of sound in air plus speed of observer divided by speed of sound minus speed of source. This will give us the answer we're looking for because they're moving towards the same direction, and the standard formula is what we're going to use. So let's go ahead and plug in our values and solve for the apparent frequency. In this very case, we have that our frequency of source is 1000 hertz, 1000 multiplied by the speed of sound in air is 343 plus the speed of the observer, which is 10, all over 343 minus 20, which is the speed of source. Okay, so our frequency prime is equal to 1000. Let me work on the fraction. 343 plus 10 will give us 353 all over 343 minus 20 will give us 323. All right. So let's go ahead and use our calculator to divide these two values to get the correct answer. 353 divided by 323 would give us frequency prime is equal to 1000 multiplied by 1.093. Okay, so this is what I'm getting, 1.093. And if we continue this way, we have that frequency prime is equal to 1000 multiplied by 1.093. For clarity purposes, let's use our calculator. Times 1.093. So this is giving us 1093. This means that the apparent frequency as observed by the observer as they were both moving towards each other is 1093 hertz. Alright, and this makes sense because they're moving towards each other. So the frequency should be higher than when it's moving away from the observer. And this is the very first part of the question. So let's go ahead and solve the second part. For the second part, the question says, if the observer stops, what will be the new frequency? Okay, so if the observer stops and the source is still moving towards the observer, we expect that the apparent frequency will be higher than the frequency of source because the source is moving towards the observer in this very case. It's not moving away, but still towards. And we also expect getting a value higher than 1000 hertz. So let's work it out and see if we can get the answer that we expect. Okay, but in this case, we cannot use this formula because the observer is stationary. It says if the observer stops. If the observer stops, what will be the new observed frequency? So in this case, our apparent frequency will now become, this now becomes 0 because the observer has stopped, while every other thing remains the same. So this will also remain the same. You might ask me, why is this still negative since the source is moving towards the observer? Yes, because positive multiplied by negative is also negative, so that is why this one remains unchanged. So let's plug in our values and see if we can get the right answer. But the reason why this one changed is because the velocity of observer has changed. As the observer is now stationary, he's no longer moving. Therefore, it has to be 0. Okay, our frequency prime, which is the upper frequency, now becomes, so for this one here, it's 1,000. That is the true frequency of source multiplied by 343. This is the speed of sound in air divided by 343 minus the velocity of source, which is 20. So what do we get here? Let me continue this way. Our frequency prime will now be equal to 1000 multiplied by 343 all over 343 minus 20 gives us 323. Okay, so let's go ahead and simplify this part to get the value that we're looking for. So we have 343 divided by 323. What do we get? We're getting frequency prime is equal to 1000 multiplied by 1.062. Okay, so we're getting 1.062, and our frequency prime is equal to 1000 multiplied by this value will give us 1062 hertz. All right, so you can also see that this solution also gives us a value higher than the true frequency of source, and that shows that as the source approaches the observer tends to hear the higher pitched sound. But if the source were moving away from the observer, we would definitely get a number lower than 1000 hertz. That is it for today. Thank you for being there, and thank you for watching this video till the end. See you next time.